this video, we want to talk about the Boxcar-Big-Omega formula, which is a very, very compact solution to the Three Indistinguishable Dice Puzzle, a problem posed by Matt Parker on his YouTube channel, Stand Up Maths. So a short summary of the problem: we have three dice that we cannot tell apart encased within a larger transparent die. The larger transparent die gets rolled, and with that, the other three dice. And we want to use such a roll of these three dice to simulate the roll of two dice while preserving all relevant probabilities. The fact that these dice are enclosed within a larger die just means for us that we cannot get at them. We cannot remove one of the dice. That would be the easiest solution. But we're looking for a mathematical solution to this problem, and that's what we're going to look at right now. It's called the Boxcar-Big-Omega-Formula. Now, why is it called that? Well, we're using boxcars here, so in other words, double sixes, to refer to the number 12, and we're using the omega, the big omega function from number theory, which is just the function that counts the total number of prime factors of a number, counting multiplicity. So in other words, for example, big omega of 12 would be 12 is 2 times 2 times 3, so it would be 3. Right? It just counts the prime factors regardless of whether they're repetitions or not. Okay, that's why it's called the Boxcar-Big-Omega formula, because we use big omega and we use boxcars to define a certain term that will be used in determining the answer. So this is the entire method. Let's take a look at a couple things that we might not understand yet. For example, we have three values of a roll, so V1, V2, and V3, so that there's nothing difficult about that. In minimal clockwise order, so we'll need to know what that is. And they have something called neighbor distances, A and B, so we'll need to understand that. So minimal clockwise order is just a way of putting our roll in order. This is the crux of the matter, actually. If we can put our values in a good order and in a convenient order, in a useful order, then the rest of the problem becomes quite easy. So let's take a look at what minimal clockwise order means. First of all, we need to define distance for our situation here, and that just means the shortest path between two values on the dice clock, and this is what I'm calling the dice clock. So in other words, the distance from 5 to 1 is not 4, but 2, since that's the shorter path. And we say that a roll is in minimal clockwise order when the clockwise span between its first and last value is minimal. So in other words, if I had the roll 5 and 4 and 3, let's say. If I had 5 as my first value, then I would have to span, how many hours is that on the clock? 1, 2, 3, 4 hours on the clock. However, if I were to start, for example, at the 3, I would only span 2 hours. So in that case, this would be our minimal clockwise order: 3, 4, 5. Now we can talk about the neighbor distance. That's also something very similar. Let's actually look at the example we just did. Let's say we had a 3, a 4, and a 5. Then the neighbor distance would just be this distance here. So from 3 to 4 would be a 1, and from 4 to 5 would also be a 1. So the two neighbor distances would be 1 and 1. And we'll also be using the neighbor distance product, which just means that we're going to multiply these together. So let's go back and, well, actually let's do an example here. Let's say we had the roll 2, 3, 6, maybe 2, 3, 6. So we can look at these values, 2, 3, and 6 on the dice clock, and we can see that the closest way of grouping these together, in other words the minimal clockwise order, would be starting at 6. Because if we started at 3, for example, we'd be going all the way around the clock back to 2. So the order must be 6, 2, and 3. And we'll take a look back here. 6, 2, and 3 is exactly what it is. Okay, so now we can go back and look at this method again. So we needed to understand a couple of things in order to be able to do the method, but the method itself is very compact, as I said, very compact. So we have 3 values of a roll, v1, v2, and v3. Additionally, we define a 4th value, which is just the average of these two. And it is these 4 values, v1 to v4, that we're going to be using to create a 2-dice roll. So we compute this term here, Boxcar-Big-Omega, and use that to determine our 2-dice simulation. So if the neighbor distances A and B are equal to 0, then our 2-dice simulation is simply Boxcar-Omega and 2 Boxcar-Omega. And if it's not equal to 0, then we use V1 and V sub Boxcar-Big-Omega. Now that sounds a bit complicated, but it's a lot easier than it sounds. So let's do a couple examples. Let's say we rolled a 4, 4, 4. Then the neighbor distances would be 0 and 0. We multiply them together and create this term here, or calculate the term rather. Big omega of 0 plus 12. Boxcars just indicates 12. So I need to know big omega of 12. I've got a little list over here. That is equal to 3. So in other words, Boxcar-Big-Omega is equal to 3. And since we're in this case here, a plus b is equal to 0, right? We know that our roll is Boxcar-Big-Omega, which is 3, and then 2 Boxcar-Big-Omega, which is 6. And that's exactly what we get, 3 and 6. Okay, another example. Let's say we rolled a 4, 4, 5. The neighbor distances would be 0 and 1. We put them in to the formula for Boxcar-Big-Omega. Again, we have big omega of 12, which again gives us 3. In this time we're in this case here, which means we use V1 and V sub 3. So in other words, value 1 and value 3. So we use 4 and 5, which is exactly what we get here. Now let's do the next example. Let's say 6, 1, 2. The neighbor distances would be 1 and 1, right? So we put that into our formula. We're looking, in other words, for big omega of 13. Since 13 is a prime number, that's an easy one, so that gives us 1. In other words, the index we need is 1. So we should use V1 and V1. So in other words, a double. We use the first value twice, this 6, and that's what we get, double 6. Okay, a couple more examples. Let's say we have a 2, 3, and a 5. The neighbor distances would be 1 and 2. The product of those we put into this formula for Boxcar-Big-Omega. In other words, we're looking for big omega of 14. 14 is 2 times 7. So it has, in other words, 2 prime factors. So that gives us our index of 2. In other words, we use value 1 and value 2, which in this case is 2 and 3. We'll do one last example. Here we have 1, 3, and 5, neighbor distances 2 and 2. Sub that in. We are looking, in other words, for big omega of 16. 16 has 4 prime factors. Our index is 4, so we use value 1 and value 4. And remember we said before, value 4 is just the average of values 2 and 3. So the average of 3 and 5 is 4, so that's 1 and 4. So that's Boxcar-Big-Omega, very compact. Now, no one said that this was an especially practical way of performing this 2-dice simulation, right? There are simpler ways. I have other videos with things that are easier to remember. But this one I think is interesting because it is so compact. We're only computing one term here, Boxcar-Big-Omega, and we use that to compute all 216 possibilities. But don't take my word for it that this actually works. Let's take at least a short look at why and how this works, and that it indeed works at all. So just a short review of the probabilities involved. There is only one way of rolling a double 1, for example, where there are two ways of rolling a 1, 2, or a 2, 1. Right? We signify that with a colon and a number. Same thing goes for 3 dice rolls. Right? There's one way of rolling 3 of a kind, 3 ways of rolling 2 of a kind, and 6 ways of rolling 1 of a kind. Again, signified by a colon and a number. So, since there are many more 3 dice rolls than 2 dice rolls, in fact there are exactly 6 times as many, we will need to send exactly 6 3 dice rolls to each 2 dice roll, as we have done in this example. If we roll, for example, a 1, 2, 3, then we say we are simulating the 2 dice roll double 1. And since this is 6 times as much as that, the probability works out. As you can see here, it reduces to be the same fraction. It turns out that that works for this entire map here, this entire table. I call this the dice clock map because we're dealing here, as we talked about before, with distances on a clock. And dealing with distances on a clock allows you to preserve a lot of symmetry that you wouldn't otherwise be able to preserve. It allows you to see similarities between rolls that you might not otherwise see. For example, 2, 3, 5 is like almost a straight, right? It goes up 1 and then up 2. And 3, 4, 6 goes up 1 and then up 2. So you can see that those are related. And you can also easily see that 1, 2, 4 is related in the same way, right? It goes up 1 and then up 2. But you might not think about the roll 4, 5, 1 as being related, since we don't usually think of the distances going over the borderline from 6 to 1. But if you do, and indeed think of them on a dice clock, then you have a lot of nice symmetries to play with when you're making your map. So let's just do a couple of examples, just random examples. Let's say we have 1, 3, 3 here. Okay, so the neighbor distances are 2 and 0, and we want to compute boxcar tau, which is just tau of 2 times 0 plus boxcars, so plus 12, which is big omega of 12, which, since 12 has 3 prime factors, right, 2 times 2 times 3, is 3. So in other words, we need not only V1, we also need V3. So we need the 1 and the 3. And that's what we have here, the 1 and 3. Let's do another random example. Let's say we had triple 2. Well, that would mean we had neighbor distances of 0 and 0. Let's put that within big omega. And then we're adding boxcars. And again, we're dealing with big omega of 12, which again is going to give us 3. But this time, since a plus b, so in other words, since the neighbor distances sum to 0, what we need to use is Boxcar-Big-Omega itself and 2 Boxcar-Big-Omega. And we saw that this was 3. So that must be 3 and 6. And we see, indeed, 3 and 6. So, that is the Boxcar-Big-Omega formula. And that is compact, isn't it?